Today we're gonna go through chapter 2, which is word vectors and word senses right here. So basically, it's more. So in the first kind of chapter, we actually give you guys kind of like really kind of general introduction in how to represent the words into like transform transform the text into numbers, how to represent the words using the matrix, and how to actually put the matrix into models and actually do a lot of prediction and classification. So we mentioned one kind of model which is word to vec. So today we're going to actually dive a little bit deeper into that model and give you guys more like a detailed introduction explanation on this kind of model here. So basically I really like Google Colab, which is more like an online like Jupyter notebook right here. So I use it for the notes taking. So most of the time, I'm actually just gonna put all the formulas and all my notes here. Sometimes I'm gonna use my iPad kind of like a notes and handwritten notes over there. But for today, I'm gonna actually go through this kind of notes here. And I really kind of recommend this kind of platform to you guys. If you just want to do like simple sandbox or kind of like a trial session or some kind of experiment on the project, you can actually use this. Or you want some kind of explanation along with the code you were writing here. But if you just wanted to actually run the entire project, which are going to cost you a lot of memories, I don't actually personally recommend this. So this is more like a sandbox and like experimental kind of platform you can actually use for the Python kind of like coding and also kind of project running stuff. So back to the lecture. So last time we talked about like a word to vec here, and we stopped at the gradient descent over there. So I wouldn't mention what is gradient descent, but basically this is like a most classic, definition we use for optimization, right? So this is how we optimize the loss function and try to find the local minimum and try to find the final kind of like optimal solution to the model, which is how we solve the model and get the parameters. So basically, gradient descent is just like it's kind of like updating rules or updating kind of like principle. It's just like the new kind of parameter basically equal to the old parameter minus a learning rate times the first order derivative of the loss function with respect to the parameters here. So we can like repeat that several times and try to find. We actually goes from the top of the mountain and try to slide down a little bit until we get to the bottom of the mountain, and then we got to find the final parameters we want to use for the model and the final kind of solutions to the model here. Okay, so that's gradient descent. But this, to be honest, like this gradient descent is actually barely used these days. Like I don't see any kind of like tech firms actually use this. Because this is really, I wouldn't say it's cliche, but it's more like an old-fashioned kind of like a concept which has a lot of like flaws and disadvantages. Probably doesn't really work for all kinds of different purposes. So based on top of this kind of concept, we actually have another concept which is called stochastic gradient descent. So why do we actually use stochastic gradient descent, and what kind of like a gradient descent is this? So the gradient descent, if you look at the gradient descent right here, so basically this is the formula. So the biggest problem actually is embedded in this. For example, I'm going to use my iPad here, just show you guys one example here. So for example, let's do this. For example, let's think about linear regression, which actually has the ordinary least square. So for that kind of example, think about, so I'm gonna actually write here. So for that example, think about this way. Type. So let's think about linear regression model, which is really simple, like y equals to beta 0 plus beta 1 times x1. Okay, so that's really simple, kind of like a regression model, right? So we only have two parameters, like beta 0 and beta 1, two ways here. Okay, so suppose we have 1, 2, 3, 4, 100,000 kind of like samples. Suppose that's the sample size we have. So when we do the gradient descent, so suppose we are doing gradient descent for beta 1. Beta 1 nu equals to, using the same kind of formula we had right here, beta 1 old minus learning rate alpha, right, times the first order derivative. Okay, so the problem here is the first order derivative. So first order derivative of ordinary square, basically I remember is like it's a summation of y minus yi square. So it's really hard to write in this way. So it's the loss function. Let's write loss function here. Basically the sum of from 1 to n, from 1 to 100,000, right? So it's from 1 to 100,000 here, and y minus this part to the power of 2, right? That's a loss function. And we try to make the first order derivative with respect of this, with respect to beta 1 here, And after that, you should have, remember, first order derivative should be the sum again, from 1 to 100,000. And we have x1 times y minus beta 1. So make a first order derivative with respect to beta 1 here. So beta 1 x1, yes, equal to 0. Okay, so that's basically the first order derivative with respect to the beta 1 here. So, or I can write it down here in this way here. Let's write here. So it's gonna be the summation, from 1 to n equal to 100,000, and it's gonna be x1 here times y minus, sorry, it should be beta 0 here. I've got a beta 0 minus beta 1 x1, and you try to make that equal to 0. Okay, so that's a first order derivative, which you're gonna plug it back in here. So now we have a huge problem with this part. Can anyone think about what kind of problem we have with this first order derivative? So what's the problem you think we have over here? So there must be some kind of problem with the first order derivative. Otherwise, because we don't have problem with this or that or this. So the problem must be in here so that we actually abandon this kind of concept and move to stochastic gradient descent. But what kind of problem do we have? Anyone can, share any comments on this? Anyone? So if you look at a function here, not differentiable, not really, good try. Not differentiable. Actually, we have the, it's like quadratic function here, loss function, so it's totally differentiable, right? It's actually continuous, so it's not discrete function. Yes, so basically Leyuan just said, so exactly, basically Anqi and Leyuan just said, too much data too low. So the problem here is this part, from 1 to n. I mean, you just update one parameter. You just update beta 1, this one parameter, and you have to plug 100,000 samples into the first order derivative and make this updation or make this update. how much does that cost, right? So we only have x1, one parameter. What if we have x2, x3? Then that means for each x here, one updates, just update once, you need all 100,000 samples. You need to put them into the model. So this costs a huge amount of time and also a huge amount of memory. So this is the problem here. That's why we don't actually use the gradient descent here. So instead, we actually, just like I said, so we don't use this concept anymore. We use stochastic gradient descent. And to be honest, it's not popular as other kind of optimizer like Atom or like Learn Atom, the neural network anymore. But it's still a lot of people actually using it today. So what is stochastic gradient descent? So stochastic gradient descent basically just that. Why not just about this part? Let's think about this part. Let's think about this part. Why not just like, instead of using all the samples from 1 to 100,000, why not just pick 10 samples here? Pick a mini batch, like just like a randomly select like a 100 or 10 samples, really kind of small size. Or maybe we can randomly select one sample. So basically, we try to reduce the number of the samples we plug into the first order derivative for the updates. Okay, so basically we reduce it to 10 or 100, which is called mini batch. Okay, or we reduce to 1. If we reduce to 1, basically it's called stochastic gradient descent. So we don't actually do the summation anymore. We just use one sample here and plug into this function and to actually update the theta over there. Okay, so this is called stochastic gradient descent. So one problem with stochastic gradient descent, as you might imagine, is that it's very noisy. It's very noisy because you randomly pick one sample or just 10 samples and try to update the beta over there. So usually it will take a longer time, and also the path is more like a fluctuated, like around, like it's kind of like a random walk. It's actually jump all around from here to there. So basically, it's not stable as gradient descent because gradient descent uses all the samples, but stochastic gradient descent just uses a subsample over there. But the result we care about is that as long as it can go to the local minimum and find the optimized results, that's what we all care about. So we don't really care about the process as long as it doesn't cost that kind of much of time. And turns out this kind of concept works pretty well. So basically, this is stochastic gradient descent here. So that's what we are going to use sometimes for the optimization part of the model. So yeah, so that's stochastic gradient descent. And it actually, without those huge amount of samples, it actually saves a lot of time and also memories for us. So any question or problem with this part? No? Okay, sure. Okay, now let's jump to the word-to-vec model here. So last time we mentioned like a word-to-vec model. Basically, it's used like a center word. If we just basically it's kind of narrow, instead of just focusing on the whole sentence, we just narrow into a small window, and we just look at the words inside the window, and we find the center word, we find the context word, and we try to make a prediction based on the center word or the context word. So basically, word-to-vec has two different models, which serves different kind of prediction of different kind of word types. So one of the word-to-vec, first type of model is called SG. We usually just call it SG, which is skip-gram. Okay. The second kind of model is called continuous bag of words, which is CBOW here. Okay. So skip-gram, the center kind of idea or the core idea of skip-gram is actually to predict the context word, okay, using the center word. So for example, basically it means we try to predict. Do I have an example here? Not really. Okay. Let's go back to chapter 1. I'm going to show you guys an example here. Right here. Okay. So it's going to use the center word to predict the context word. What I mean by that is, for example, suppose we're looking at this. Okay, we have this kind of window. Window size is actually 2. Okay, window size is 2 because we have 2 context word for center word. So this is a window, and inside we have the center word, which is into. And those words here are just like context word. Okay, so skipgram basically said, give me the center word into, I can predict what's the word one step ahead of that center word, and 2 steps ahead of the center word, and 1 step after the center word, and 2 steps after the center word. So that is, we fix a window, we find the center word, and we predict the previous words and you know, the afterwards word over here. Basically, those are the context word. So that's what center, that's what skipgrams you know, is gonna do here. So that's basically the idea of the skipgram. So what's kind of like steps we're gonna take, you know, to actually do this kind of model, to actually construct that kind of model. So basically, first of all, we have to create 2 matrix here. The first kind of matrix is we here, and second matrix is you here. So we here, which is the input word matrix. Okay, so it's the input word matrix here. So the ith column of the we is actually, you know, n-dimensional embedded vector of the word I. So what does that mean? So basically, we is all the words vectors you're gonna put into the model. Okay, so I'm gonna actually show you in this way. For example, let's draw, yeah, let's just draw the matrix here. So the we matrix is gonna look like this. This column here represent the word A. Okay, so A basically is a vector. Okay, and the vector size could be, for example, it could be 4, it could be 8, it could be 16, all depends on you. So it could be 1, 0, 2, 4. Okay, so basically it's a unique kind of encoding or language you put or to transform the A, or it could be any other numbers. You could do a binary, you know, encoding, or you can do other kind of encoding. So basically, each single word here is 1 column, and this column is actually a vector that has a lot of numbers inside. And those numbers together construct this kind of single word. So if you have a word kind of like a vector that has dimension 4, that means this dimension here, the row dimension is going to be 4. Okay, it's going to be 4. Okay, so basically that's we here. So for U is actually the output word matrix, output word matrix. So since we mentioned like input word matrix, what is the input here for skipgram? What is the input here for skipgram, like model here? Are we going to use all the words, or we are just going to use some of the words? Any idea here?
Is it only the central word?
Exactly. We only use the center word. So all the words here is going to be the center word. Okay. So U here is the outward matrix, is the output word matrix, which is a context word. So it's going to follow the same kind of rules here. Okay. It's going to follow the same kind of rules here, but it's the row that is going to be the n-dimensional embedded vector of word G. Okay. So previously here, for this one here is a column, but here is going to be the row. Okay. So basically, this is a context word matrix. Context word matrix. Okay. So what do we do here? First, we generate our one hot input vector here for a center word. So basically, is that, so how do we actually generate a we here? So we actually, first of all, we I'll draw it here. So first of all, let's construct a word matrix. And this matrix has all the word, and this is called X. Okay, had all the word, or you know, whatever name we just give it. For example, this is word 1. This is word 2. Each column is a word. Okay, and until word N. Okay, so what do we do here is we construct one hot input vector. For example, 0, 1. And you know, 0, 0, 0. So only the second kind of like component is 1 here. Only the second kind of component is 1 here. Okay. If that's the case, or you can do it this way. You can do another one, 0, 0, 1 here. Okay. So basically, that's one hot encoding vector. So first of all, you're going to construct that, and this 1 here means this is the position where the center word is going to show up. Okay, so the second word is the center word. All the other words are context word. Okay. Second, we got our embedded word vector for center word. We see which is v times x. So which is this kind of input word matrix we have and times this. So think about it this way. If we just time this with this, and this. Think about this, and we just try to multiply this with this kind of matrix. What can we get in here? For example, this is say this is 1 times 4, and this is 4 times 4 times 4 word here, and each word has a 4 dimension. At the end, we can get 1 times 4 matrix, right? We can get a 1 times 4 matrix. But what does this mean? That means we only select the word center word here. We only select the center word that is in this position. Other word multiplied by 0 will turn into 0. Okay, so that's basically how we select the input input word matrix here. How we actually got an input word matrix over there. Okay, so after that, we are going to generate a score kind of vector. So that's the next step. So we are going to multiply the generated input word matrix with output word matrix here. Okay, output word matrix here. And we multiply that. That's because for the skipgram, kind of model, we actually use this function as a probability function for prediction, which I will mention later. Okay, so we're going to generate a score function, and then we're going to put this kind of score function into a softmax, and we try to maximize. Next step is actually try to maximize the softmax function, try to get the optimal prediction for the context word. Okay, so what I mean here is, first of all, I'm just going to give you a one-hot encoding vector, and I'm going to give you all the word. Basically, you do a multiplication. You select this center word matrix, which is small vc here. Okay. Next, I already have the output word matrix over there, right? I actually multiply the center word matrix with the context word matrix. Okay. So after this, I'm going to put that into my loss function. My loss function is right here. So basically, that is giving the center word. I'm going to predict the possibility of all the context word with window size m, and its function going to look like this. Okay, so on the numerator is actually the multiplication of the center word with the specific context word you try to predict, and in the denominator is actually summation of all the multiplication of the center word and the context word. Okay, this is the softmax function. Okay. Does anyone doesn't know softmax function, or you guys already know what softmax function is? It's basically exponential divided by the summation of exponential, and it has a value from 0 to 1. That's basically why we use the softmax function here. Do you guys all know softmax function? No? Okay. Where should I start? Okay, so why do we actually use the softmax function? First of all, what we do here is we try to predict the possibility, right? So what kind of range do we have for the possibility? 0, 1, right? It must be greater than 0, but it must be smaller or equal to 1, right? So we need to find a function that actually going to put the value into this range. So basically, this function serves that kind of purpose. Because here is a summation of all the exponential, here is a specific exponential. So basically this is the proportion. So it must be between 0 and 1. Okay. So basically what this loss function going to give us is what's the possibility of the first context word next to the center word? What's the probability of the next context word next to the center word? For example, what is the possibility of this? What's the possibility of that? Giving this kind of center word. So we want that possibility here to be between 0 and 1. Okay, so that's why we use softmax function. And why do we actually use multiplication here? That's because we try to use the cosine similarity between different kind of word vectors. For example, why do we use multiplication? Think about the we see here. So I actually mentioned this in the previous chapter. Let me find it here. So why we actually use multiplication? I mean, think about the two words that are two numbers. If the two words are the same, they're totally the same. They are the same number value. Word 1 is 3, word 2 is 3. Their multiplication would be 3 times 3, which is 9. What if they are not the same? One is 1 and one is 3. Then their multiplication is much smaller, right? So basically, why we use multiplication? That's because we try to measure the similarity. And the multiplication tells us how big the difference is going to be for the angle between these two different kind of vectors over there. Okay, so together, put that on top of the exponential function. This is the Softmax function. Okay, that's why we use this for the possibility prediction. Okay, is that clear? Anqi, right? Anqi, is that clear for you? All good? Kind of. Okay, maybe we can talk later if you have more questions. But basically, that's a Softmax function. It's a function we're going to use for a lot of prediction. Actually, if you try to make a multi-class classification, most of the time the default kind of like a loss function is Softmax function. But if you try to do a binary classification, so probably the function you're going to use is the sigmoid function. Okay. So we'll talk about that later, but this is actually a really common kind of function we use, like a simple function we're going to use for a loss function here. Okay, so basically what do we do next is we put the multiplication here into here, and we optimize this kind of function. We do the first order derivative and we do the SGD, stochastic gradient descent, and then we find, we try to find the optimal kind of like vectors of the context word and center word over there. Okay. So I'm just gonna give you an example here and see, let's see how that works. For example, oh, I made a mistake here, actually previously. The we here, the input word matrix is all the words, it's not just the center word, okay? The we kind of input word matrix is all the word. The small we here is the center word matrix, okay? Let's look at the example here. Suppose this is all the words I have. I really like you, Daniel. That's all the word we have. Or maybe you don't like me. Anyway, so this is a word matrix here. And suppose I'm going to do a binary encoding. You can do other encoding, but I'm just going to do a binary encoding. And each word here has a dimension 1, 2, 3, 4, 5. 5 dimension here. And I have 1, 2, 3, 4, 5. 5 words. 5 times 5, that's actually the input word matrix here. And this whole column represent I, and this second column represent really, and this column like, so on and so forth. Okay, so next, what we're gonna do? So next part is, so that's what I mean previously. Next part is we're gonna generate our one-hot input vector. For example, the center word I wanna use is like. That means if that's the center word I wanna use here, if that's the center word I wanna use, that means I'm gonna put that into 1. And the other kind of component here as 0. Okay, so next we're going to do a multiplication of this times this. So if we do that, that's going to be this times this, this times this, and this times this, right? At the end, we're left with this. We're left with this, which is exactly like the center word. And this is the center word matrix. Okay, that's how we get our center word matrix. Basically, you do a binary kind of one-hot encoding, and you only select the center word matrix as the input word matrix here. Okay, so the U here is is actually output matrix over there, just like what we told previously. Then you multiply those two together, you get the score function. And for the graph, for a neural network kind of like a perspective, it looks like this. This is the one-hot encoding you just generated. And this is all the word matrix. You multiply this with this, you select the center word. And you pass the center word to all the context word. You multiply it with all the context word here. So this is the first layer, that's the second layer, and this is the final layer. And you try to maximize this loss function. At the end, you get a possibility, of which one has greater probability. For example here, for this context word, we have possibility 7%, 1%, 5%, so on and so forth. And the largest number is 70%. So this row corresponds to the position of a specific context word. So for example, if this row corresponds to this word, Daniel here, it's going to give you that word. So for that word, it's going to be 1. It's going to show you that kind of specific, kind of like a word over there. Okay, so on and so forth. So basically, that's how this kind of like skip-gram model works. Any problem with this part? I'm pretty sure you guys probably have a lot of questions. It's okay. We can stop here. And if you want to discuss a little bit. All good? No question? Not at all?
Hi, sorry, I have a quick question here. So,
Sure, go ahead. Yeah.
It looks like, so the output of, the skip grams, after the whole process is over, the output is still in very high dimensions, I guess, because is it still the same as the one hot encoding?
Oh, yeah, that's a good question. So suppose we have 5 words here. What do you think the final dimension of the possibility is going to be?
Is just one row, but like 5 rows, 1 column.
5 by 1, exactly. That's it. That's it. Exactly. Basically, that's it. So it totally depends on how large a window size is you're going to use. Okay. So it's going to tell you for example, suppose this is the 5 numbers, right? So it's going to tell you what's the number. For example, it's going to be 10% here, 20%, 30%, and last number is 70%. So for that specific number, I'm going to predict this is Daniel. Okay. So yeah, it could be a huge size. It could be a huge size. It totally depends on the window size. But usually the window size we use are very small, 5 or 10. We don't use that huge amount of window size because if you expand a window size too long, you're probably gonna lose some memory, right? So if it's too long, then I can track the first word, I can track the last word. But since there's a lot of like explanatory word, 就是 lot of like 定语或者说在哪里, so where and when. So those words doesn't really matter. Or there's some kind of word the or he or she. If those kind of words are in the middle, it doesn't really work that well. So basically, we try to contrast, like try to compress the window size into a small kind of like a window, so that we usually won't have that kind of large size. But that's a super good question. Yes. Does that answer your question over there?
Yes, thanks.
Yeah.
I guess, sorry, another question is I'm looking at this graph right here and the W matrix.
Yeah.
So that's not the one hot encoding result. Or sorry,
no,
that's not.
This is not a one hot encoding. Basically, each column here is a word, and each word is kind of encoded in some way. So it totally depends on you. You can use a different kind of encoding. I use 101, but most of the time we don't actually use that. We use some specific number to actually encode the specific word vector. So a single word could have the dimension 100 or 10 or 2 or 5. It totally depends on you. It depends on how you want to encode that vector. Yeah, so basically those kind of numbers here is one word. So a word is not a specific number. It's actually one column of number. Yeah.
Okay, and the dimension of each word, like the encoded vector for each word, can be different from.
It can for each word is actually the same. It's actually the same. So for example, this is word 1, this is word 2, that's word 3.
Right.
So all of the word are gonna have 6 times 1, which is like dimension of 6 vector of the 6 component inside.
Yes, but it could be different from. It could be irrelevant with the window size or something.
No, it doesn't.
It's the same.
No, it doesn't really. No. If you look at the dimension here, What we do here is 1 times 5, right? We use a
Yeah.
one-hot encoding, which
Yeah.
is here 5 times 5 and 5
Yeah.
times 1, right?
Mhm.
So what's the size of this? How do we decide the 5? It's totally depend on the word dimension, not the window size,
Oh, gotcha.
right?
Okay.
So even here is like 6 times 5.
Mm-hmm.
It takes 6 times 5. At the end, you're going to get 6. So
Yeah.
basically, the final result is always final result is correlated with window size. But in the middle steps, that kind of dimension of the word is canceled away. Do you know what I mean? Yeah. So it's not a big deal here. Yeah.
Okay. Thanks.
Yeah. Very good question, by the way. Thanks. So basically, let's skip Graham. Any other questions here? Okay, let's keep going. So that's skip Graham. So next part is continuous bag of words. So I don't really want to go to this kind of like specifically because it basically uses the same kind of logic, but now we kind of like doing the reverse part. That is, we use a context word to predict center word. That is, giving all the words here, problem, turning, banking, crisis, giving the forward, I'm going to predict what's the center word here. Okay, what's the center word here? But the steps basically is the same. So like the road here. First of all, we generate a one hot wording vector for the input context of size m here. Okay. So previously, remember, we just want to extract the center word. So it's a one vector. But now since we want to extract all the context word, so we need to generate a matrix instead of one hot encoding vector. Okay. So now here, you're going to have a lot of like 0, 1, 0, 1, 0, 1, like sparse matrix. You extract the context word matrix here. Okay. That's a context word matrix. And again, you can do an average. So this is another trick. You can do it or you cannot. You can actually, because you try to scale all the matrix and make them in the same range, but it totally depends on your task over there. At the end, we're still going to multiply the context word with output word or the center word matrix here not center word matrix, the output word matrix to get the score function. Then we put it back to the Softmax function, maximize or minimize the loss function, and we get a final kind of result over there. So basically follow the same kind of logic, but I think I can show you the graph of that. Remember seeing here. Yes. Let's skip gram. Yes. So see, for skip gram, you only have one x, which is specifically a vector here, and you have a huge input word matrix here. But for the continuous bag of words, because you try to use a context word to predict the center word, that means you're going to have a lot of 0, 1 and one hot encoding to extract a specific context word. But after that, it's all the same. It's all the same, as you can see here. Okay, it's actually all the same. So basically, you kind of reverse order. You kind of like doing 1 to multiply words or multiply word to one word. Okay, so I'm not going to repeat that part. So let's skip that part. Next part, negative sampling. Negative sampling. Okay, so this is like a technical problem we actually have with the word-to-vec function. So if you actually look at the possibility here, okay, the possibility here is actually the specific exponential of the square function divided by the summation of all the exponential square function. The computation of the numerical or numerator here, not numerator, actually, sorry, it should be denominator. The computation of the denominator here is actually a huge problem. For example, what if we have 20,000 words? What if we have 100,000 words? Just like a stochastic gradient descent, that means we're going to do all the words. We're going to multiply all the words together to get this summation. That's a huge amount of calculation. So how can we actually do to reduce those kind of amount of calculation? That's why we're actually going to learn about negative sampling. So basically, what do we do here is we keep the numerator. We keep the numerator as a true pair, which is a center word and a word which exactly in the context window. Okay, and we try to maximize the inner product between the words. But at the same time, instead of going through the entire corpus, instead of going through all the specific windows, we try to actually randomly select some of the specific windows. Not like previously we loop through all the windows. We just randomly select some of windows over there, which is not the same as a true pair. Okay, we select really some kind of bad windows over there for the model to learn. So the model knows, oh, this is really bad window, and true pair is actually on numerator. So that in that way, we actually make a contrast between, you know, the better kind of windows and true windows over there, and for the model to learn. Okay, so basically it's the same. It's kind of similar to stochastic gradient standard. We don't actually use a lot of the entire corporate summation, which or all the windows. We use a specific non-true pair windows for the denominator. In that way, we can actually reduce the amount of calculation over there. Okay. So basically, that's what negative sampling is doing over there. Okay. Any problem with this part? Any problem with this part? So basically, when you do, I think there's a like when you use actually use a library of virtual vectors, it's gonna give you a negative sampling kind of like argument over there, so that you can specify how many kind of random samples you can select. What kind of like rules you want to put, or the customized function can put into negative sampling to select those kind of like noisy kind of windows over there. Okay, so that's negative sampling. Any question about that part? Okay, so the way we actually sample the irrelevant words or the bad kind of windows over there, the default one, of course you can use your own kind of like, you know, kind of like rules over there, but the default one is actually, it's called a 3/3 kind of unigram distribution over there. Okay, so basically the function is going to be like this: pw equal to uw to the power 3/4, and this is a uniform distribution, and divided by that here. Okay, divided by that here. So basically, this function is going to be more often to sample the real words otherwise, because sometimes, you know, we will sample like the word like Z or A as a stop words, but we actually never sample the irrelevant words, like, you know, really kind of rarely seen the words. So sometimes we do need to capture, you know, some kind of like a rare words we don't actually use that often. So we don't actually really want to care about those, like a Z and those kind of words. Those are always irrelevant. But we want to capture some really, really bad words, which is totally irrelevant to the true pair window over there. So this function is going to help us to do that. But this is not a must. I wouldn't say this is a must-know knowledge, but if you want to know more, you can go back to my notes, to previous notes, and try to actually keep it more kind of like, you know, try or kind of reading yourself. But just remember, this is the default function, and its purpose is actually try to make the less frequent words to be sampled more often than before. Okay. So basically, that's where to whack kind of models over there. It sounds like a little bit complicated, but once you understand all the logic, it's basically very simple. It doesn't actually involve a lot of complex part. Okay, so back to the model comparison part. Previously, we talked about how we actually, you know, represent a word in chapter 1. That is, we actually count how many times each word shows up in the specific window. Then we put a specific number into a word matrix over there. So this is called frequency or count-based kind of model over there. Okay. So for this specific model, I'm pretty sure a lot of you guys may have heard about this LCE, latent semantic analysis, or hyperspace analog of language, HAL, or Henninger PCA. Okay, so this one, I believe some of you guys may have heard about it. So it's more like one subversion of the PCA principle component analysis. So those are more like a count-based kind of models. So it basically is based on the number of times each kind of word show up in the matrix. So I don't really care about what kind of order the word is gonna be, you know, put into the window. I don't really care what's the next word, what's the previous word. I only care about how many times you show up in the word. Because the core idea is like, as long as the two words show up really frequently into in the specific text or specific sentences, I have the reason to believe those two words are going to be correlated somehow. Maybe it's the analog, maybe it's like contrast word. Okay, So this is a Convex kind of models over there. I didn't actually go to this specific model because it truly depends what kind of project you're working on. But most of the time, I don't actually use those kind of models. Because why? Because one of the reasons is that a primer used to capture similarity instead of other patterns. So you can use a word for similarity. For example, if you just want to do a really simple recommendation system on a products, like you want to recommend to the consumer, and you want to see how often apple and banana are going to show up in the same basket, yes, you can do this, but it's not that precise. What if you just want to predict, what kind of product this consumer doesn't really like? It's really hard to do so. Okay, so it's basically to capture word similarity instead of other patterns, like for example, I not only just want to know the similarity between the two products, but also I want to know why the consumer actually choose the two products. If you want to know a deeper kind of like meaning or intuition behind that, this model doesn't actually tell you anything about it. And also it gives, like a really huge importance to the words with large counts. That is, because this model is based on the, the frequency of the words, like how many times the words show up in each kind of context or each kind of sentences. So the more frequent the words show up, the more important it is, right? But does that really mean that a word is a word you really care about? Like I or she or he or other kind of words? Not really. Does that kind of word gonna give you a lot of information about the entire context? Not really. So this is some kind of like specific disadvantage this type of model has. So it cares more about the frequency instead of the true meaning of the specific word over there. But it do have some kind of advantage. For example, trains really fast because you just don't need to pass the entire matrix into the model once, only once. You pass the entire matrix, just like me and what's her name? I can't remember. Just like what we actually talked about previously. We just need to pass the entire kind of input word matrix into a model once, and we're done. We don't have to use it like twice. So basically, it trains really fast, and it just doesn't actually cost you a lot of time. Actually, and another kind of advantage is that it uses statistic very efficiently. So basically, we look at a co-occurrence matrix, right? So we can always, try to use that kind of like a covariance or the correlation between different kind of like occurrence of the word to actually make some prediction or classification. Another type of model, which is what we learned today, skipgram, CBOW, or word2vec, or those RN recursive neural network, window by window, and Softmax, those kind of like what we talked about previously. Those are more like semantic word meaning or like context, focused like a model. So in that way is we don't really care about how many times the words show up in each window. What we care about is what kind of role you are playing as a center word or context word in the window. That's what we care about. We care about your meaning, your explanation. So the advantage of that is generate, improved performance over the downstream task. For example, like an entity recognition, speech tagging. Because for speech tagging and entity recognition, we don't really need to know how many times numbers show up. We care more about what a word means. For example, I just want to capture the location of specific sentences. So the location might only show up once. Like I live in London, that's probably the only time that London show up over there. If you really count that number, how many times London show up in the sentences, it really doesn't give you any information. So it's more like a window. The context can capture that kind of specific location, and also capture the complex patterns beyond the word similarity. So it captures because it uses a window. It cares about the meaning. It cares about the whole kind of window's meaning and a word meaning. So it can give you more like explanation on the word itself instead of just a series of like occurrence numbers. But the disadvantage of that is that this kind of model scales with the corpus size. Just like the other girl like you mentioned previously, although the window size is not huge, but if this matrix get really large, suppose we have 100,000 words, when you pass the entire corpus into a neural network, it's still going to cost you a huge amount of time. So it actually scales up with, kind of input word matrix and also with output word matrix, because you're going to multiply the same kind of word matrix, get score function, right? So that's one of the disadvantages over there. And since the model actually goes through the words sample by sample, it doesn't really make efficient use of statistics. So what does this mean? This means we don't really care about the number of times each kind of word actually show up, how many times this word show up in the window. So we only care about meaning, but we can like try to get around the occurrence part. So in that perspective, we didn't actually fully use that statistic for the prediction over there. Okay, so basically that's a comparison between two different type of models. Which one's better? It's hard to say. It's really hard to say. It depends on the task you're looking at. Depends on the project purposes. But those are still those days are very commonly used kind of like models here. Okay. Any problem with the model so far? All good. Any question? If you have a question, we can stop here and discuss a little bit. Are you guys still awake, or you guys just fall asleep? I'm joking, by the way. All good?
Hey, Daniel, do we have any examples?
Examples? Actually just show this example. So you want me to kind of go through this kind of example again for you?
No, I mean like I think this is kind of simple example. I mean like in real application, like.
I see. Okay. Sure. But I cannot really show you because previously I had an internship in Air Miles. We actually use the word to back a lot. But I cannot really, I think I showed you before, yeah, I can give you like a really general example how that works. So basically, the goal is actually, previously we have a lot of data. The data we have is basically for each consumer, we have then the products that a consumer purchase, because we have the Air Miles data. Like if you're Air Miles member, we know what kind of product you purchase every day, every month, or every year. So basically, we don't want to use a price. We don't want to use a quantity. We just want to use a product description. And we try to think about, can we actually grow the consumers into different groups and try to figure out the preference of specific consumers over there. So a core idea here is that since we only have the product description, why not just start from the simplest model? Why not just start from word to web? So basically what do we do here? For example, me and Shelley, suppose we are the two consumers and we have two baskets over there, right? So for each basket, we're gonna count how many times each single product gonna show up in our basket. Okay, for example, if banana show up 5 times and banana also show up like 5 times in Shelley's basket, that means we probably gonna share the same kind of preference, with respect to banana. That is, we both like bananas. Okay, but if I have a lot of chocolate that show up a lot of times in my basket, but chocolate only show up once in Shelley's basket, then I'm gonna say, oh, we probably have different kind of preference with respect to chocolate. So in that way, we use the occurrence of the products throughout the year, throughout the months, and we try to capture the similarity between different consumers' preferences. And we also try to capture the similarity between different basket and shopping purposes. Okay, I hope that could explain the the count-based model a little bit, occurrence, right? But yeah. Just like we talked about previously, that's not precise at all. Even if Shelley purchased 5 times, 5 bundles of the banana on specific day, or specific month, I purchased 5 bundle of banana in specific month. Maybe it's just a coincidence, right? Maybe we just happen to purchase the same amount of banana, or maybe it's because of promotion, because it's super cheap, so we actually both purchase a lot. So from that perspective, it's not that precise. So basically it tells you something, it tells you some kind of correlation, but doesn't really give you the precise correlation or what is the rationale behind the consumer's shopping kind of behavior over there. Okay, so that's why we're going to switch to the direction prediction or the context-based kind of word kind of windows or the model, so that we try to figure out what this product means to you, means to me, and Shelley specifically. What does banana mean to me? Do you like it or not? What does a banana mean to Shelley? Do you like it or not? So basically, it's more like about the product itself, the meaning of the product to each consumer, to each basket, instead of like the number of times each kind of like product show up in the basket over there. Yeah, basically that's an example I can come up with. Does that actually convince you guys a little bit?
Yeah, that makes sense.
Okay. Yeah, it's really interesting because most of I wouldn't say basically retailing kind of like firms like Loblaws or Walmart or Air Miles or Loyalty One, all those kind of like firms over there. Most of the time, we don't really have the price and quantity, and we don't really want to use that because the price and quantity sometimes is kind of like correlated themselves. So it has some kind of endogeneity problem in itself. We don't really want to use that kind of some features. So more of the time, we think the product description is more reliable. Basically, it's kind of reflection of your preference somehow. So most of the firms, at least to my best knowledge, they actually use a lot like NLP on the product description and try to actually figure out the preference of specific consumers. Yeah. Okay. How much time do I left? We started at 1:43. Okay. I think I'll still have half an hour and see whether we can finish this part. So previously we talked about the advantage or disadvantage of the two type of models. So maybe you have another kind of like question is, can we actually combine the two models into one model? Can we actually take the advantage of one model or the positive side of one model and positive side of another model and combine them into one model? And the good news is yes, we can. So this model, which combines the two models together, the occurrence-based model and the context-based model, is called GloWAC. Okay, so this model was invented. I have to mention this guy. He's a genius. It's invented by Chris Manning. Okay, he's actually I don't know. He's like a god to me because he's like a frontier soldier or whatever, like experts in the NLP and deep learning kind of area. So he has a lot of really famous publications. He found a lot of words, and he's he also is really good at telling stories. So this model is actually invented by him and this person. Okay, so those are just like those are just co-author the kind of project between those two persons. So what is GloWAC? GloWAC basically means we care about the currents, but we also care about the context. So we try to combine those two together. So what do we do? So we start with a specific kind of example here. I mean, think about those kind of words: solid, gas, water, and random. And think about the specific possibility of a word given ice, or that is, for example, for this one, think about the possibility of solid given ice. How much possibility do we have for that word to show up given ice? It's going to be a relatively large number, right? And think about the gas and stream. Those two words going to show up together. Yes, it's probably large. But ice, gas, or gas, ice, not really. It's kind of small. So basically, this model is kind of borrow. So from this perspective, is it actually borrow a little bit of, the context word and center word, kind of like definition there. So basically, borrow that part. Basically, I'm going to actually look at all the pairs of the possible kind of like, kind of words over there and see, what's the possibility of the two words actually show up, or given what one word is over there, and what's the possibility of another word show up over there. And that's not the end of the story. Besides, I'm gonna do, kind of like a ratio. So not only look at specific window, specific words, but now let's do a relative, not just like absolute value. Let's think about relative. What's the importance of the solid with respect to ice compared the solid with respect to stream? What's the importance of that way? Try to think about the relative importance of two words. So this is actually from the word-to-vec part. So this is the positive side of word-to-vec part. Another part is it actually borrows is a co-occurrence matrix over there, which is how many times each kind of single word show up in a specific word window or document. So basically, it's going to use a co-occurrence matrix. It indicates the number of times the word J occurred in the context of word I. So basically, I have a bunch of the context word window, and now let's do a window, occurrence matrix. For a specific window, let's count how many times each word going to show up, given a specific word. Okay. After that, we combine those two together. Okay. So here it's just a single word, right? Let's transform the single word into a matrix and do this kind of like a ratio again. That is, given word I, what's the possibility the word J is going to show up given that word, which is a ratio of this here. Okay. So what is Xij? Xij indicates the number of times the word J occurred in the context word I. Okay. So basically, that's how we actually represent this. So it's a combination of, it's a combination of possibility, but also it's a combination of the occurrence. So in that way, kind of combine the two part into one here. Okay. So basically, what we do here is we try to pick up two words here and compare their relative importance and make it into a possibility ratio. And we take a natural log of that. Okay. After that, so that's our first step. Second step is we don't actually throw away the context word and center word kind of like, definition we used previously. We're still going to use that. So we're still going to keep this, which is context word and center word. Okay. So basically, this is the Softmax function that computes the possibility of word J showed up or appears in the context of word I. Okay. So it's Qij. So we have the Pij, we have the Qij, right? So what we do here is, why not just make a difference between the two? Make a difference between the two. Because this is more like a, occurrence-based like a possibility given the specific word between A and B, right? This is more like context-based like a possibility between between these two specific words. So, or you can think about it this way. This is observed possibility. That's a real possibility because we just calculate a number of ourselves here. And this is more like a predicted possibility using context-based like model. If the difference between the two is really small, that means, yes, we are getting to the right point. We actually got to the right model. We actually got to the right parameters. If the difference between the two is huge, that means, no, we don't really actually, got a lot of, we actually got a lot of difference between predicted and observed, kind of like a multiplication or score function. So basically, as the end of what we do here is actually, times those with this, because we try to get a score function. So we times this output or input matrix with this, and then we try to minimize, this kind of loss function. So basically, like I said, it actually takes both sides, like occurrence, but also occurrence is here, Xij, but it also takes about the possibility with Pij and Qij here, which is from the context part. So after that, we're gonna minimize this kind of model, and we try to extract, the most meaningful word or for prediction word classification over there. Okay. So here. So previously we have Xij here, but we changed that to Fxij. So basically, this is kind of like a think about this is Xij. Previously is like input matrix, but here we just transform that into a weighting function, because this function could be huge. That could be a huge kind of function. We try to transform that into a smaller dimension function that is gonna give us like specific like values. For example, here it just gives a value either 1, 0 if it's 0, or like this one here, it's either 1 or it's this value here. So instead of previously we have the whole matrix, now I'm gonna, it's gonna tell me what's the possibility what's the possibility or the share of each kind of difference or the residual is going to contribute to the entire loss function. Okay, so this is like, the residual. Ignore the square for a second. This is the residual. The observed minus the predicted. So what's the difference between your model and a reality? And this is like a weight. This is a contribution of this kind of residual to the entire loss function. So we actually, since it's a weighting matrix, why not just like, transform that into a weight, which is gonna give you two values, either it's one or this value, right? So in that way, you don't have a huge dimension anymore. In that way, you can actually transform that into this, okay, this function here. And we're gonna actually make, maximize or minimize the negative of this function, try to find the optimal kind of like parameters we have over there, okay? So yeah, this is how the function look like, the weighting matrix over here, okay? Basically, it's kind of reverse ReLU, like the ReLU function. ReLU function is like a, reverse the part of this, but this is more like, another side of ReLU function. So basically, it's like an increasing function until it reaches the max level of x max and turns into 1. Because we try to make the value between 0 and 1 because it's a weight, right? So that's why we pick this specific function here. It can only be between 0 and 1 here. Okay. So from that way, you can actually get a little bit of sense that we actually combine the context-based model and a occurrence-based model into one model, which is GlobeVac model. So this model is trained really fast because it only uses it actually uses the entire matrix here, this one here. It uses the entire X only once for the P here, right? So it doesn't require a lot of memory, so it trains really quickly, and it's scalable. So even you have a huge kind of corpus, we can still do that. Because at the end, we care about kind of weights, not a specific xij here. So it's scalable, and also it has good performance even with small corpus. So this is what the author said. He actually shows this kind of result in his paper, which is GlobeVac paper, like a suggested reading in the first chapter. If you're interested, you can go there and check it out. So yeah, basically that's everything for today. I'm gonna keep this part for the next lecture. Any problem here with respect to the GlobeVac model here? If you have any question, you can ask, because that's the last part of today's lecture. Basically, yeah, that's everything for today. Any question, any comments, concerns, or discussion you wanna have right here?
So for these different methods, are they in the same Python package or they're in separate ones?
I think they are in separate kind of package over there. And I to be honest, I haven't tried this before, but let me try GlobeVac. Library.
So yeah, for GlobeVac, I've used that before. So normally you can use a pre-trained model and then fine-tune it. So there's PyTorch or TensorFlow or Keras.
I think it's PyTorch. I saw that in PyTorch or TensorFlow before, but I don't think it's in Python library, right? Yeah.
Yeah, it's in like all the Keras, TensorFlow, or PyTorch has the library. They have pre-trained model and then you can fine-tune it.
Right? Yeah, I think so. Yeah. Globe here. Yeah. Basically, yeah. I think you can use Python. No, actually, I think you can use Python to run it, but it's not going to work as quickly as the TensorFlow or PyTorch over there. But I think you can still use a notebook to run this part. Yeah.
Okay. Yeah.
Question.
Sure. Go ahead.
You may have covered this, but I may missed it. So what do we use to evaluate the results of like the embeddings? Like how do we know one embedding result is better than the others?
That's what I'm gonna tell next lecture actually. So we have we have actually two evaluations. One is called intrinsic evaluation. So basically this one is more like offline evaluation. So basically you try to through a random words inside and try to make it a trial experiment. So relatively speaking, it's more like a smaller sample. It's not a huge sample. It's not like a reality part. So this is more like, within the team, within the company, let's keep it confidential, keep it like a private. Let's just test and specific kind of samples. For example, it depends on the task. If you just want to try to predict for example, the context word given the center word. So probably we're going to extract some kind of like a random context from Wikipedia, and we throw into the model and we see how that works. But usually it's like a small random trial kind of like sample over there. So that's one kind of like evaluation over there. So basically the goal of that kind of intrinsic evaluation is really simple. It's just try to test whether the model works for the specific subtasks, just like I had here, specific intermediate subtask over here, okay? But this is not an end story, because if you want to put that into production, you have to do the extrinsic evaluation over there. Basically, that is, so this is for the model itself, so it's more like absolute value or absolute perspective of the evaluation. For extrinsic evaluation, basically you have the offline, not offline, baseline model. For example, you just make a prediction based on the global frequency of the word. You don't use any kind of model. We just count how many times each word show up in the entire corpus. You're going to put that word as a prediction. That's the baseline model. Or you have another baseline model. Basically, you can compare different kind of models and see which one works better. And basically, you have to show that your model actually wins out most of like the tests over there. That's how you actually can do this type of extrinsic evaluation. Or sometimes we do A/B testing. For example, back to the product description, like example I talked about previously. For example, I constructed this kind of like a recommendation system based on the preference prediction between two consumers. I put this kind of like a recommendation engine on like attached to a specific website. I actually select a bunch of people, right? Like A/B testing, a control group and treatment group. I'm gonna recommend them, using the recommendation engine, but only for the treatment group. For the control group, I'm gonna use a global or baseline model, right? So now you have the difference between the two, and just try to collect the data from them, see their kind of reaction, and see whether there's a huge difference between their purchasing behavior or their kind of reaction to this kind of like a change between different versions of the recommendation engine. Yeah, so that's more like a reality side. So intrinsic evaluation is more like, I wouldn't say it's not a reality, but it's more like a trial experimental kind of stuff. It's intermediate subtask here, but extrinsic evaluation is more like production side. So we have to put this into reality and test out how the consumer reacted to that. Yeah.
Okay, cool. Thanks.
Yeah. Any other questions over here?
Hi, everyone. I have a question outside the scope of this course, but it's Python related.
Mm-hmm.
So when you're importing a CSV file, but the CSV file contains different columns and different rows. So when I use read CSV, then you just put everything into one column, but that's not really what I want. How do you solve this problem?
You put everything into one column. Oh, I see. Because you didn't actually parse. You actually didn't parse those kind of values inside that column. So you have to use like a parse or argument over there. It's either comma or space. So let me show you. I'm going to show you the read CSV. So if you actually go to the like a documentation of here. I think it's this one, delimiter. So basically, you just tell the system how do you want to parse, the different kind of like, because in a previous like CSV file, you're probably gonna put everything into Le Yuan just mentioned here delimiter. You probably put everything into one column, like using comma to connect them. So basically, you have to parse them. Here use a delimiter.
Okay.
Yeah.
Cool. Thanks.
Any other question here? No? If there's no question, please go back and finish assignment because it's due next week. I'll talk to our quote by quote CEO, Shelley, to discuss how we actually should upload the assignment to the Google Drive. And I hope you guys have a nice Sunday or nice night for the Toronto friends over there. And hope you guys will stay healthy indoor and take care. Make sure you wear a facial mask when you go out. And other than that, that's call this a day. Thank you so much, and I hope to see you guys next week. And don't forget to sign up for the spreadsheet. Okay, all right. I'll see you guys next week. Bye.